In this video, we're going to study isotopes. So you've heard of isotopes before, but it's great to review them because now we're going to take a look at isotopes in the grade 11 context. And we're going to do calculations with isotopes as well to see what they're all about. So here are our learning goals. We'll have to be able to define what an isotope is, calculate relative atomic masses of an element using something called isotopic abundance, and then distinguishing between isotopes and radioisotopes, and also giving examples of radioisotopes as well. So we're going to start off by going through this presentation and then going to the handout and filling in some blanks together and doing some practice problems. So in nature, when you look at elements on a periodic table, the elements that you see there can exist in a few different forms. For example, when you look at hydrogen, in reality, hydrogen on a periodic table, let's hide this, is not just one type of hydrogen. When you look at it, you'll notice on the periodic table that the mass is 1.01. And so we wonder why there's sort of a decimal value there. And that's because hydrogen can exist as sort of a light version of itself, kind of in between version of itself, and a heavier version of itself. So you can have this light hydrogen, this sort of medium hydrogen, and this larger hydrogen in terms of mass. They're all still hydrogen because they all still have, see the atomic number over here is 1, 1, and 1. So it's still just one proton, one proton, one proton. And you'll notice that also if they're not ions, they have the same number of electrons, 1, 1, 1. The only place they really differ is the amount of neutrons that they have, which is what makes them have a different mass. So for example, this hydrogen over here, hydrogen with a mass of 1, does not have any neutrons. It's only a proton. This hydrogen over here has a mass of 2, and so it has 1 neutron. And this hydrogen over here has a mass of 3, which comes from the proton and the 2 neutrons. So isotopes are essentially the same element, but just different versions of the same element. And by different versions, we mean that they have different masses. And those different masses are because they have different number of neutrons. So for the most part, the isotopes of an element have almost identical chemical properties. They can have some slightly different physical properties based on different masses, of course, but for the most part, they're very, very similar to each other. And so the reason they have similar chemical properties, though, is because they have the same number of electrons and protons. So at the end of the day, they react roughly very similarly to each other. So these are isotopes of hydrogen over here, and they do have different names if you want to get technical. So protium, deuterium, tritium, those are all different names for the isotopes of hydrogen. And this is just one particular type of example. Here we can see isotopes of carbon. And so if you look at the data table over here, you'll see that all these isotopes of carbon, they all have 6 protons because they're all, at the end of the day, carbon, right? Proton determines the identity of the element. Their atomic number is all 6. Their electrons, assuming it's neutral, would all be 6 as well. But where they differ is their mass, right? So this is carbon, we call this one carbon 10. So carbon dash 10, that means carbon with a mass of 10. Here we have carbon 11, carbon dash 11, carbon with a mass of 11, carbon 12, carbon 13, carbon 14. And so the reason that they have different masses is because of, well, the only thing that's different between them is the number of neutrons. So carbon 10 has 4 neutrons, which makes sense because 4 neutrons plus 6 protons is 10. Carbon 11 has 5 neutrons, which makes sense because 6 plus 5 is a mass of 11, and so on and so forth. You'll also notice that these isotopes here, another area where they're different is that some of them are stable and some of them are radioactive. The radioactive one, due to their structure, number of neutrons, protons, and a balance there, they will break down over time, sometimes very rapidly, and they're not very abundant in nature as a result of that because they break down. So if you see radioactive, that's essentially what that means, and you'll delve a little deeper into that as we move forward. But here's just another example of isotopes specifically for carbon here. And when you do name isotopes, you put the name of the element, dash, and then the mass there. So then we have to ask ourselves, which isotope is, well, most abundant? Which one is there more of in, let's say, nature? And there's actually a term for that. It's called the isotopic abundance. It's basically how common is a particular isotope of a particular element in nature. So over here, we have, again, carbon. And here we have the mass of carbon. And so we often wonder, well, where does this mass come from? Like, which mass do we choose? Do we choose a mass of, carbon 12, carbon 13, or carbon 14? And so the answer is really that we take an average of all the different types of carbons that exist in nature, and we use that as the mass, that average. But it's a weighted average, so it's not all of these are weighted the same. Not all of these are found in the same percentage in nature. For example, if you look over here, carbon 12 is much more abundant than, let's say, carbon 13 and carbon 14. So the mass is much closer to carbon 12, 12.01 is closer to 12 than it is to 13 or 14 because there's just more carbon 12 there, right? It's kind of like if you had a mini quiz and a big test, let's just say. The mini quiz is not worth a lot, and the big test is worth a lot. So your final mark at the end, let's just say it was only based on those two assessments, would be closer to whatever you got in the big test compared to what you got in the little quiz. And that's because a big test is just worth more. It has more of a weight, let's just say. So it's the same idea here, even though, so it's the same idea here because 98.9% of carbon in nature is carbon 12. That mass here, the average mass is going to be closer to carbon 12. So it's a weighted average, we say. Okay, so we take a weighted average, and that weighted average is basically related to the isotopic abundance, which is essentially how the amount of a given isotope of an element that exists in nature, how common that isotope is, and we express it as a percentage. So the isotopic abundance of carbon 12 is 98.9%, carbon 13 is 1.1%, and carbon 14, well, less than 0.1%, because as we saw in the previous slide, it's very unstable. So, as I mentioned previously, the mass that you see on the periodic table is not the mass of just one of these isotopes here. It's an average of these isotopes. It's a weighted average of the isotopes. So we don't just count them all equally. The one that is most abundant, has the highest isotopic abundance in nature, is going to have a bigger say in what the final mass is going to be here. So that's why we call this the average atomic mass. It's a weighted average. This is not the mass number. When we round the mass to do those calculations with neutrons and protons and electrons, that rounded number is called a mass number. The number you actually see on your periodic table is the average atomic mass. We just round it to make it more convenient for our calculations. So we're going to take a look at, well, how can we figure out this average mass using isotopic abundance and a few other bits of information as well. So just a little comparison between the average atomic mass and the mass number. These are all different terms for average atomic mass, by the way, so atomic weight or relative atomic mass. So again, that's what you see on the periodic table. It's a weighted average of all the isotopes of an element, and it's still measured in atomic mass units. And that's what, again, the periodic table contains. The mass number is specific to an isotope. So when we round, let's say we rounded this to 12, that's the mass number of carbon 12 in reality. Um, so isotopes of the same element, when you study them, they're going to have the same atomic number, but they're going to have a different mass number. So for example, the mass of carbon 12 is 12. That's its mass number. The mass number of carbon 13 is, well, 13. The mass number of carbon 14 is 14. So we can express standard atomic notations for isotopes as well in a similar way that we did for really any element. We just have to put the specific mass. So if we go back here, for example, here's just standard atomic notations for the different isotopes of carbon. They have the same number of protons, 6, 6, and 6, but we put their mass number up here. We put the mass number. So that mass number is the mass for, well, carbon 12, and this is the mass for carbon 13, and this is the mass for carbon 14. So again, mass numbers on the mass number is not on the periodic table. That's just when we kind of round that it's for a specific isotope. The atomic mass or the average atomic mass is on the periodic table, and it represents the weighted average of all the naturally occurring isotopes, the ones in nature. It's a weighted average. So we're going to take a look at how to calculate the average atomic mass using some data and information provided. And so we'll do that on our handout as we fill in some blanks as well. So just to show you over here, I'm going to show you the setup of the problem, and then afterwards we'll go try to solve it. So what we've given you here is we've given you information for the isotopes of silver. We have silver 107 and silver 109. These are two naturally occurring isotopes of silver. And so you'll notice that they both have the protons or atomic number of 47 and 47, making them silver. But they have a different mass. This has a mass of 106.9, and this one over here has an atomic mass of 108.9. And so what we want to find is what is the average mass that we will put on the periodic table. And so here's our formula to do that, and I'll walk you through that as we go forward. The other thing you'll notice as well is we've given you the relative abundance of each of them. So in nature, 51.8% is this silver 107, and 48.2% is this silver 109. So we're going to go ahead and solve that problem after we fill in some blanks together. So let's go to our handout over here. And let's see what we can fill in. Let's see what we remember from the lesson that we just saw with the slide deck. So isotopes are atoms of the same element that have different numbers of which subatomic particle, protons, electrons, or neutrons of neutrons. And because they have different numbers of neutrons, they therefore have a different mass. And so the various isotopes of an element have almost identical chemical properties because they basically have the same number of electrons and protons. There might be some differences in physical properties, but that's the basic idea behind it. They're very similar in chemical properties. And so as we saw from the slideshow, this is just some example of isotopes of hydrogen that exist in nature. And the mass you see on the periodic table is an average of those isotopes, of their masses, a weighted average though. But just to show you, this is the standard atomic notation for each one of them. And they all have the same atomic number, the 1 there, but they differ in terms of the mass that they have there because they have different number of neutrons. And so if you want to write this out, for the protium there, the lightest hydrogen, you could write H1. For deuterium, you could write H2. And for tritium, you could write H3. Or if you want to write it with a name, you could write hydrogen -1, for example, and then -2 and -3 for the other ones. Okay, but it's kind of the same idea there. So there's a term that we have to define called isotopic abundance. Let's see if we can get the blank there. So the amount of a given isotope of an element that exists in nature expressed as a percentage of the total amount of this element. And here we can see some examples. We can see there's carbon 12, carbon 13, and carbon 14. And the isotopic abundance of carbon 12 is 98.9%. So in nature, the carbon that you find, if you took a teaspoon of carbon, 98.9% of that carbon would be carbon 12. 1.1% would be carbon 13, and 0.1% or even less would be carbon 14. And here we have the standard atomic notations for the different isotopes. Once again, take a look. Since they're all carbon, they all have the same atomic number of 6, but they differ in terms of their mass number. So just to show you, carbon 12, if you want to find the number of protons, well, we have 6 protons over here. It should have 6 electrons as well because it's neutral. And if you want to find the number of neutrons, you're just doing your 12 minus 6, and that gives you 6 neutrons. But if you want to look at carbon, let's say 13, still 6 protons, still 6 electrons, but the number of neutrons would differ because you have a mass that's higher there. So you'd have 13 minus 6, which is 7 neutrons instead. So that's the heavier version of carbon. So what do you see on the periodic table? On the periodic table, for example, when you look at a mass, you see this decimal number. And so what you're seeing is the average atomic mass. That's the weighted average of all the natural isotopes of that element. So that weighted part there, what does that really mean? It just means that the one that's more abundant, that has a higher isotopic abundance, has a higher say in terms of where that average is going to be, right? It just has a higher weight. It's worth more because there's just more of it. That's why, for example, the average mass of carbon is closer to the carbon 12 mass compared to 13 or 14, right? 12.01 would round down to 12, for example. So that's why we take a weighted average. And so here we can see a difference between the terms average atomic mass, atomic weight, relative atomic mass. These are all kind of the same term here, and mass number. If you remember, we were rounding the average atomic mass when we were calculating the number of protons and neutrons and electrons just for convenience. When you round that mass, what you actually get is you get a mass number. In reality, the mass number is the mass for a specific isotope. Like, for example, this is the mass number for chlorine. This is 35 for chlorine 35. So if you were to write that out, you write chlorine 35. This is a mass number for chlorine 37. But the average atomic mass of chlorine in your periodic table, it's number 17, is 35.45. It's a weighted average of the isotopes that exist. Okay, so that's just a little refresher in terms of what the average atomic mass is. And I do want you to go over radioisotopes in a bit more detail. So they're isotopes that aren't very stable, and so they undergo decay. So they basically break down spontaneously, and when they break down, they actually create different elements, and they release other radioactive particles like alpha radiation. And so you can find more information about radioisotopes in this video here. I do want you to watch it. And I also want you to write down some examples of some applications that you see in that video as well. And you can take some notes about the video as you watch it and use this figure here to help you understand radioisotopes in a bit more detail. So in the next video, what we're going to do is we're going to do some sample problems together. I'm going to show you how to calculate the average atomic mass that you would see in the periodic table using the atomic mass of the individual isotopes and the isotopic abundance, also called relative abundance. Just before we sign off from this video here, I do want to show you a quick, on the periodic table again, where the masses are. So if we open up a periodic table here, you'll notice once again that all of the masses that are provided have decimal places, and that's because it's not the mass of a specific isotope, but rather the weighted average of all the isotopes that exist in nature.